Hello everyone. In the beginning of the class, let us look at new announcements. Okay. So the first new announcement is May 16, 2022 class videos uploaded. Hello everyone. I have uploaded the class videos on May 16, 2022 to YouTube. Their URLs are this, and this. Okay, best regards, Wei Zhen. Okay, the second new announcement is the slides of Chapter 4 has been updated, version 2022-0518. Hello everyone, I have uploaded the latest version of the slides of Chapter 4 to the eCourse 2 website. The location and the file name are eCourse 2 website, multiple input, multiple output techniques for wireless communications. Course content, slides, Chapter 4, slides 2022-0518.pptx. Best regards, Wei Zhen. Okay, the third new announcement is the handout of Chapter 4 has been updated, version 2022-0518. Hello everyone, I have uploaded the latest version of the handout of Chapter 4 to the eCourse 2 website. The location and the file name are eCourse 2 website, multiple input, multiple output techniques for wireless communications. Course content, handouts, Chapter 4. Handout 2022-0518.pdf. Best regards, Wei Zhen. Okay. Next, let us see the progress of the last class. Okay, in the last class we have taught to Chapter 4 slides, page 16.3, and go to figure 4.2. Okay, please open the slides of Chapter 4 and please go to page 16. Okay, the feature with the largest scale in this plot is the linear trend towards lower received power when the power and the distance are plotted in dB. Okay, so we can see that in figure 2, the largest scale in this figure is this line. Okay, so this line is the linear trend towards lower received power when the power and the distance are plotted in dB. Okay, so we can know that the distance is plotted in dB and the received power is plotted in dBm. Okay, so not in dB. Okay, this component is denoted by the dashed line. Okay, this line, okay, the dashed line in figure 4.2. This linear behavior is often observed in real channels, which indicates that the received power tends to decrease with the inverse of the distance raised to some power, so-called power law propagation. The second largest scale observed in this plot is depicted by the light solid curve, which is referred to as large-scale fading. Okay, let us go back to this plot. So in figure 4.2, we are talking about this curve. Okay, the light curve. Okay, which is the large-scale fading. Such fading, which is sometimes called shadowing, is normally due to large objects along the propagation path that block some of the transmitted radio frequency energy. Lastly, the smallest scale feature, called small scale fading, is denoted by the thick curve. Okay, let us go to figure 4.2 again. So this curve, the thick curve, is the small scale fading. Okay. The small scale fading, which is characteristic of a non-line of sight multipath channel, is caused by constructive and destructive interference. Okay, what is constructive and destructive interference? Let us see the handout. Okay. So we are on page 19. Problem 1. What is constructive and destructive interference? Solution. In physics, interference is a phenomenon in which two waves combine by adding their displacement together at every single it is strange. I press nothing. Sorry. Okay, point in space and time to form a resultant wave of greater, lower, or the same amplitude. Constructive and destructive interference result from the interaction of waves that are correlated or coherent with each other. Okay, if you have taken the course Digital Communication, I think you should have learned the coherent detection or the coherent detector. And in the midterm exam, we also have a problem, that is problem 2. Okay, to plot the simulation and the theoretical bit error rate of non-coherent binary phase shift keying under a Rayleigh fading channel. Okay. Either because they come from the same source or because they have the same or nearly the same frequency. Interference effects can be observed with all types of waves. For example, light, radio, acoustic, surface, water waves, gravity waves, or matter waves. Please see figure 9. Okay, let us see figure 9. Okay, figure 9 shows the interference of two waves. When in phase, that is, two waves have the same phase. The two lower waves create constructive interference left. Okay, so these two waves create constructive interference. resulting in a wave of greater amplitude. Okay, this wave, which has a greater amplitude. When 180 degrees out of phase, they create destructive interference. Right. Okay. We can see that this wave is like a sinusoidal wave. Okay, like for example, sine of t. Okay, and this wave, okay, is like the graph of the equation sine of t minus pi, okay, or plus pi. Okay, and after adding these two waves together, okay, they will be cancelled, and we will have a wave with amplitude which is always equal to 0. Excuse me. Okay, so let us go back to the slides. Okay, constructive and destructive interference between signals arriving at the receiver over different paths resulting from potentially different propagation mechanisms. Okay, because the different paths have different lengths, okay, different path lengths, so the time from the transmitter to receiver are not the same for different paths. Okay, since the time are not the same, so the phase may not be the same also. Okay, so we will have constructive and destructive interference. Okay, in general, MIMO performance is primarily affected by the largest scale, which impacts the value of rho, and the smallest scale, which impacts the statistics of H. Okay, for this reason, we focus on these two propagation components in the remaining sections. Okay, that is, we only consider the larger scale, which is called the path loss. Okay, and we also consider the smallest scale, which is the small scale fading or the multi-path fading. Okay, so we do not consider the shadowing, okay, which is also a part of the large scale fading. Okay, next let us go to section 4.2, power law propagation. Okay, power law propagation depicted by the dashed line in figure 4.2. Okay, let us go to figure 4.2 again. Okay, in figure 4.2 we can see that there is a dashed line, okay, which represents the path loss, okay, which is a part of the large scale fading. Excuse me. Okay, go back. Can take on various properties depending on the nature of the wireless channel. In general, the received signal power PR can be computed using the Friis equation named after Harold T. Friis. Okay, please see reference 32. Okay, reference 32 is a paper which is written by H.T. Friis. The title of the paper is A Note on a Simple Transmission Formula, which is published in Proceedings of IRE in 1946, okay, which is a very old paper. Okay, go back. Which has the following form. Okay, PR is equal to PT times GT times GR, over L prop of D. Okay, where PROP is the abbreviation of the word propagation. It is a function of D. Okay, and times L other. It is a mistake. The equation number is not in the correct location. Okay, let me fix it. Okay, good. Okay, where PT denotes the transmit power, GT and GR denote the antenna gains of the transmitter and the receiver respectively. So please note that the transmit and receive antennas also have their gains. Okay, L prop of D denotes the propagation loss when the distance between the transmitter and the receiver is D. Okay, L other denotes the other losses due to all sources other than propagation. For example, cable losses. Okay, what is cable losses? Let us see the handout. Okay, it is page 23. Problem 1. What are cable losses? Okay, solution. Relative cable loss is defined as the amount of power dissipated in the cable divided by the amount of power provided at the source side of the cable. Okay, let us go back to the slides. Excuse me. Okay, cable losses. Antenna pointing loss. Okay, what is the antenna pointing loss? Okay, let us see the handout. Okay, problem 2. What is the antenna pointing loss? Solution. When a satellite link is established. Okay, antenna pointing loss can occur not only in the case of a satellite link, but for the other type of communications. The ideal situation is to have the Earth station and the satellite antennas aligned for maximum gain. Okay, there are two possible sources of off-axis loss, one at the satellite and one at the Earth station. The off-axis loss at the satellite is taken into account by designing the link for operation on actual satellite antenna contour. Okay, what is antenna contour? Okay, let me show you a figure. Okay, because it is difficult to find the definition of antenna contour on Google, so I think I only can show a figure to you. Okay, let us see the first figure. Okay, this is the contour plot of the actual ratio in dB. Okay, the antenna is excited by okay, let us click into the website. Okay, this figure. Okay, the antenna is excited by a dipole source. Okay, if you do not understand what is a dipole source, it is okay, because it is not the key point here. Add some x0, y0 and 0, some coordinates. With the polarization, we will introduce what is the polarization later in the handout. angle of theta on the xz plane. The dimensions of the gold rectangular antenna are as follows. Okay, A, B, D, okay, etc. Okay, so let us see. This is a contour plot. Okay, so the x-axis is x in millimeter, and the y-axis is y also in millimeter. Okay, and the color denotes the gain of the antenna. Okay, so represents the actual ratio of the antenna in dB. Okay, from when the color is blue, okay, the actual ratio is 0.5 dB. Okay, you can see that in the center of the contour plot. Okay, and when increase, okay, to blue, light blue, green, yellow, orange, okay, red, and to brown color. Okay, when the actual ratio is equal to 3 dB, the color is brown. Okay, like this, the outer part of the contour plot. Okay, so this is the an example for the antenna contour. Okay, let us go back to the handout. The off-axis losses at the Earth station is referred to as the antenna pointing loss. Antenna pointing losses are usually only a few tenths of a decibel. Okay, let us go back to the slides. Okay, antenna pointing loss, and the next is the implementation loss. It is very difficult to find the definition of the implementation loss on the internet. Okay, it spent me several hours to find a proper definition of the implementation loss. Okay, let us see the handout. Okay, problem 3. What is implementation loss? Solution. Speaking strictly, the interpretation of implementation loss is loss that is unaccounted for as measured as the bit decision point. Okay, here is the reference of the solution. Okay, under different place, for example, different website, different web pages, different books, or different papers. Okay, you may see different definitions of the implementation loss. So I cite the reference to indicate where did I find the definition. Okay, here. Okay, let us go back to the slides. Okay, next page. The signal to noise power ratio ρ is obtained by dividing PR by the noise power as follows. Okay, ρ is equal to PT GT GR over L prop of D times L other times K times T null times F times B. Oh, the equation number is in the wrong place. Okay, let me fix this problem. Okay, equation 4.2 here. Okay, good. Okay, so please note that PR is equal to PT times GT times GR divided by L prop of D D times L other. Okay, it is 25 minutes. Let us take a break.